record all 4 lectures, and I've already screwed that. I've already screwed up in the second attempt, but so we can get an idea of what this looks like by drawing some pictures. Okay, I'm going to try and draw. It doesn't really matter what you put down here for G of F. This is our original spectrum. Okay. Going to have it say it has a bandwidth of A. So again, same representative spectrum for our baseband signal that we used throughout the course. Okay, it's just in an arbitrary shape. Now, what is this? Well, this is nothing more than a shifted version of this. It's shifted to the right by Fs, then when n is 2 by 2Fs, then by 3Fs, and then they're all scaled by Fs. So if I draw this, I'm going to say, Fs is out here. So 2Fs would be out here. So what this now looks like is this. These would actually be AFS. They'd all be the same height. And we'd have the same back here at minus Fs. Okay. This would be now the spectrum of our ideally sampled signal. Now, just a couple of comments here. One is this thing has infinite bandwidth. So there really is no practical media over which I could transmit this thing. Even coax cable has some bandwidth, so it would filter out these higher frequency replicas. But again, this is an idealized case that we're considering, just a mathematical treatment of sampling, considering this ideal sampling. So that doesn't really bother me. Notice also that in this ideal sampling cases, all these replicas are identical. They all have the same height, they all have the same shape. Again, when we look at practical sampling, we'll see differences there. Okay. And then I have made kind of an implicit assumption here when I drew this picture. I made the assumption that Fs minus W, which would be this frequency, is greater than W, so that these things don't overlap. Which means that F of S is large enough that I've got sufficient separation between these things so that they don't overlap. We'll talk more about that. Okay. But let's say I could generate this ideally sampled case. How could I go back from this to that, which is my original spectrum? Some sort of filtering operation, right? What do I need to do to this? Bandpass or where? If I did a bandpass around Fs, that would recover this spectrum here. Okay, I could then modulate that down, mix that down, but a bandpass filter around 0 is what I want to do. That's a low pass filter. Okay. So recover G of S using a low pass filter. So with I could give it a height of 1 over Fs to undo the multiplication by Fs. Again, usually not too concerned about these scalar multiples. That just makes the signal stronger or weaker. And then this thing has to have a width of W. Okay. It could actually be a little wider than W. This would be the narrowest case, right? Because I'm not passing, the product, if this is even out here, would still be that picture. Okay. So my recovery system, actually the complete system, is G of T, and then for my ideally sampled signal, delta TS of T. Okay. And then this gets me G delta of T. So this is my generator for my ideally sampled case, and then I transmit this somehow. At the receiver, I'm getting this ideally sampled signal. I just need to low pass filter to recover G of T. So this would be my receiver, and then this would be my transmitter. Or an analog to sample converter. We could call it an analog to digital. Not quite digital, right? But analog to sample, and then a sample to analog recovery. Okay. So I imagine that you guessed that a discussion of aliasing was going to come up. Okay. So what is the condition here? To recover G of T from G delta T. Okay. Again, my condition that I don't have overlap is I have to meet this condition. Fs minus W has to be greater than W, or more simply, Fs has to be greater than 2W. Our sampling frequency has to be greater than twice. W is the highest frequency in my baseband signal. Okay. So some examples of that for CD quality sampling. They actually sample at 44.1 kilohertz, so 44,100 samples per second. That's the CD. That's CD quality, or the sampling rate that they use for audio. Does anyone still use audio CDs? You know what I'm talking about? So for CD quality, so what would be the corresponding maximum value of W? It would be 22,500. Okay, and we've talked about the audio hearing range. I think typically for CD quality, they filter out everything above maybe 18 kilohertz. And so the minimum sampling frequency they should use is 36. There's some advantage to separating these things out a little more when it comes to filtering. So, but that's consistent with what we know about high quality music, and the audio frequency range. So 44.1 kilohertz. Now the telephone company is now almost all digital. They sample for voice quality actually at 8 kilohertz. Okay. So, and I think they low pass filter out voice at around 3,500. So again, the minimum there would be a sampling at 7K. They sample it at 8K. So, but again, with you can't transmit high quality audio over a telephone, because of the sampling rates involved. It's still true even with the cell phones, because the cell phones actually are just cellular to the tower, and then tower to tower transmission still takes place over the conventional analog telephone line, or well, they're digital now, but digital telephone lines, so sampling at that 8 kilohertz rate. So let's talk a little bit more about that condition. Um, 2W is known as the Nyquist rate. So the Nyquist rate is this minimum sampling frequency. If the highest frequency in your signal's 3200, then the Nyquist rate is 6400. If the highest frequency in your signal's 20K, then the Nyquist rate is 40K. And then that's the minimum, so if you sample at any rate above the Nyquist rate, you can recover the original signal from the samples. But if Fs is less than 2W, we recover a distorted version of G of F, or really what we recover, we're doing this filtering, but on frequency domain, but what we're dealing with directly are these time domain signals, so we get a distorted version of G of T. So, what that's going to look like, bless you, I'll do my best here to draw what this looks like, but let's say this is W. Okay. And then now let's say F of S is here, doesn't meet that condition. So the easiest way for me to draw these is to first draw the individual spectra. What I really have to draw, though, is the sum. So I'm drawing them individually, but then when I sum them, I've got this region where they're overlapping. So it's fine there. And then because they're too linear, it would actually go straight across there. And then here at 2Fs, I'll have the same thing here. I'll have this, then that, and then that. Then I have the same thing here. Okay. So I'll have this, and then this. Okay. Now, yeah, this is W. This would be Fs minus W. This would be Fs over Fs over 2, that middle point. Okay. Now the smaller Fs becomes, the worse the distortion. Now so this is what G delta of F would look like if I'm undersampling. This is still AFS. Now when I run this through my low pass filter that has a bandwidth of W, what I get out would be this shape, minus W plus W, and then would be a height of A. Okay. So it's not the same as the original spectrum of my baseband message. It's a distorted version of it, right? And actually, I've got distortion at the high frequencies. So, you still may be able to hear, or the signal may still be intelligible, but you're going to have distortion in the high frequencies here. Okay, it's not going to sound like the original message because of this distortion due to aliasing. And the smaller Fs is, the greater the distortion that's present. Okay. At some point, it would become so bad that the signal would be unintelligible. Okay. Now, one thing that will actually help here, so that there's what's really going on is, because I'm undersampling, my high frequencies here are actually wrapping around and distorting my frequencies above fs over 2 are actually causing distortion in my frequencies below fs over 2 because of that overlap. Okay. So I get distortion, all the way down to fs. What would this frequency be? This is fs minus w. I get distortion between fs minus w and fs over 2. I can at least get rid of part of that distortion, not all of it, but by using what's known as an anti-aliasing filter, should always be used before sampling to limit the effects of aliasing. So I use, in the subscript here are AA for anti-aliasing. So I have my message, I run it through an anti-aliasing filter before I do my sampling. And my anti-aliasing filter is nothing more than a low-pass filter minus W to WF of AHA of F. Now, the idea there is that what I'm going to do with my anti-aliasing filter, so again, ideally you want to sample at a great enough rate, so aliasing is not a problem at all. But with my anti-aliasing filter, I'm going to filter out everything above fs over 2. Okay. fs over 2 minus fs over 2. So that now, when I'm undersampling, I'm not going to have this wraparound distortion. I'm not going to have these frequencies that are between fs minus 2 and w affecting my frequencies that are below fs over 2. Okay. I still have distortion here if I'm undersampling, but I've limited the amount of distortion. Now my picture would be like this, and then this one would abut, and then like that. And so the picture would be like this instead of the more extreme distortion I had without the anti-aliasing filter. And you can avoid both by sampling at a high enough frequency, but you always want to use an anti-aliasing filter before sampling to reduce the distortion. The anti-aliasing filter would have a bandwidth of fs over 2. So let's look at what's going on back in the time domain. We've spent a lot of time in the frequency domain. Okay. And we'll come up with what's called the interpolation formula for reconstructing G of t from G delta of t. So we've got this expression, in the frequency domain, G of f is, my low pass filter times G delta of f, right? Let's take a look at what that becomes in the time domain. Actually, so I'm going to put a little tilde over G of f here. To say this is what I get out after filtering. If I've sampled at a high enough rate and my low pass filter is correct, G tilde of F should be the same as my original G of F. But the tilde here represents that this is a signal that's gone through all of these steps. Okay. Ideally, it would be the same as the original. So in the time domain, because this is multiplication, this comes back as convolution. And we solved G delta of F. Well, that would come back as G delta of T. So G delta of F, do I still have that picture? Yeah, G delta of F is this. G delta of T is the product of my original spectrum and that comb function. So G delta of T is H of T convolved with, then I had this summation expression for my ideally sampled signal. GNTS delta T minus NTS, or taking this inside, these are just constants, n equal minus infinity to infinity of GNTS, H of T convolved with my delta is H of T. Okay. Now, what's this impulse response for a low-pass filter? So with H of F equal to 1 over Fs rect F over Fs. Now, remember, the 1 over Fs that's here was just to get rid of the multiplication by Fs here. And then here I'm letting this be, so this has width of Fs. This is our notation for the rect. So this would be from minus Fs over 2 to Fs over 2. Then H of T becomes just sinc of Fs of T. Okay. So I finally have the expression I want. G delta of T is n equal minus infinity to infinity G NTS sinc of Fs T minus NTS. Okay, that's the expression for the output of all this in the time domain in terms of the samples of my original function. And I'll try to draw some pictures. I know that's a difficult equation to visualize. Because I remember struggling with it as an undergraduate. Because it's a nasty looking kind of equation. But we do know that for Fs greater than 2W, then we've already seen that G tilde T is equal to GT. And finally letting Fs equal 2W, kind of the Nyquist rate, I get this expression for G of T in terms of, so I'm going to put n over 2W here, sinc of 2WT minus n. This is the version of the interpolation formula that he has in the textbook. Okay. So kind of what is this saying? So I've got some original GT function. Okay. I'm just going to show it here as having all positive values because it's easier to draw. And then what this says, I sample this. And part of this infinite or ideal sampling is I've got infinite number of samples in both directions. So let's call this 0. So this would be the G0 sample. This would be when n is equal to 1. 1 over 2w is TS, so this would be NTS, 2TS, 3TS. So this is the G0, but then that's multiplied by the sinc function. Okay, the sinc function here for this one sinc function, the parameters are the sinc function, so such that the 0 crossings occur at all the other sample instances. So what I'm drawing here is just, forget the summation, G0 times sinc of 2WT. That's the one sample times this sinc function. The next one is a shifted sinc, shifted by n, so it's going to be right here, and then it's multiplied by this. Okay. So it's going to have a different amplitude. Again, all of its 0 crossings will occur at the 0 crossings of the other sample. And then similarly here we have another sinc function. Okay. Now this says the original g of t here is the sum of all of these shifted sinc functions of different height. You can see that it's certainly true at the sample instances, because at the sample instances, only one of the sinc functions contributes. All the others have their 0 crossings at that instant. Okay. It's just kind of interesting that now in between, we've got contributions from all of these sinc functions, an infinite number of them. But the tails here get smaller and smaller, so it's really just maybe 3 or 4 or 5 here that are going to contribute to the sum. But the sum is such that magically in between, they sum up to give us the right values in between the sample instances. And this is all exact. And according to the Nyquist criteria, as long as we meet the Nyquist criteria, we can exactly reconstruct the original message from its samples as long as we sample at the Nyquist rate or higher, twice the highest frequency. Okay, that is it for today. We'll start looking at some of the baseband modulation methods, I think on Monday. Have a great weekend.